Welcome to session. Today we will discuss what is a couple and what is equilibrium, principle of equilibrium, then method to verify principle of equilibrium. Focus on the screen. Consider two equal and opposite forces that are not acting along same line. So this is one force, and opposite force. That's why we have taken it as negative. So both are acting in opposite directions and they are not along the same line. That is, the line of action of this force and line of action of this force, there is a perpendicular distance of d. So consider a pair of such forces which are equal and opposite and are not acting along the same line. If pair of such pair of forces is acting on a body which is shown in yellow in color, then let the body be pivoted at point O. Okay, so the distance of line of action of negative force minus F is d1 and distance of action of positive force is d2. Okay, now if we consider the moment of these two forces about the point O, which is the pivot of the body, then for positive force the moment is F into d2, and for negative force it is again F into d1. So the moment of this force is F into d2 and the moment of this force is F into d1. So if I take out common from F among this I can write it as d1 plus d2, or d1 plus d2 is nothing but d, so F into d. So this is called moment and this is called moment of couple. Now how do you define a couple? This pair of forces constitute something called as couple. So let us define what is a couple. Couple is, it constitutes two equal and opposite forces not acting along same line. So such two equal and opposite forces not acting along same line constitute what we call as couple. And the moment of such a couple is obtained by one of the forces into perpendicular distance between line of action of these two forces. So here it is d. So the d is perpendicular distance between line of action of force. This d is also called as arm of the couple. So the moment of a couple is measured as one of the forces into perpendicular distance between the line of action of pair of forces, that is arm of the couple, and its units are Newton meters or Dine centimeter. Clear? Because if this couple is acting on the body, this yellow colored body, due to which it undergoes rotation. Now from the moment of forces we can see that F into d2, this is anti-clockwise. When you see from the top, F into d2 is anti-clockwise and F into d1 is again anti-clockwise. So both are anti-clockwise. That means the body is rotating anti-clockwise. So when the body is rotating anti-clockwise, it is the moment of couple is negative. And if suppose the body is rotating clockwise, the moment of couple is positive. This is the sign convention. Clear? So the moment of couple, definition of couple is a pair of equal and opposite forces not acting along same line constitutes a couple, due to which there is a moment that is applied on the body and it undergoes rotation about a about a point of about any point of rotation. Okay, the couple has got a moment which is measured as one of the forces into perpendicular distance between line of action of forces, so F into D. So the units for moment of couple is Newton meters or Dyne centimeters, and depending on how the movement causes the body to rotate, if the body rotates clockwise it is positive movement, and if the body rotates negative it is anti-clockwise movements. Clear? Okay. Now these are a couple of examples from our daily life. So whenever we are trying to open or close a tap, we are applying a couple on the handle of the tap. So one finger will apply force in this direction, another finger will apply force in this direction. So this constitutes a couple and it causes this handle to rotate. Okay, in this case, like if we are considering this side and this side, so it is turning clockwise, which is positive. Similarly, when we try to open the lid of some jar, we are applying couple, which causes the lid of the jar to rotate and hence open the lid. So you can think about other examples from daily life. Clear? Okay. Now let us discuss the concept of equilibrium. So consider some body at rest and consider some other body in motion. Okay. If a set of forces is acting on these bodies, I am taking in random direction a set of forces. Likewise here also, like set of forces are acting. Okay. If under the action of all these forces, because this body is at rest, if it continues to be in the state of rest, then this body is said to be in equilibrium. Similarly, this body is in a state of motion. Assume uniform linear motion, assume. So it is under action of several forces. And despite the action of these forces, if there is no change in the linear motion that it is already undergoing, then this body is said to be in equilibrium. Thus, when a set of forces is acting on a body but doesn't change its state of rest or a state of motion, then such a body is said to be in equilibrium despite the action of that set of forces. Okay, so if you see in the picture, everybody is pointing gun at each other. So net result is all these forces will cancel out, and if you find the resultant of all the forces acting on the body, it will be zero. Here also the threat from each person is being cancelled out. So ultimately nobody will start shooting or trigger the shootout. So similar analogy you can think of equilibrium uh, in a body at rest or equilibrium in a body at motion. Okay, so how is equilibrium defined? When a set of forces acting on a body doesn't change its state of rest or state of motion, which could be linear or circular motion, such a body is said to be in equilibrium. Okay, so equilibrium is of two types. When the body is at rest, it is called static equilibrium. When a body is in a state of motion, it is called dynamic equilibrium. Okay, so there are two conditions that need to be met for any body to be in equilibrium. First condition is when you take algebraic sum of all the forces, that is, when you are finding the resultant of all forces, which is denoted by sigma f. Sigma means you are algebraically adding all the forces. When sigma f is equal to 0, that is, the resultant of all the forces is equal to 0. This is the first condition required for equilibrium. Second condition is when you algebraically add the moment of all such forces about some point. When you algebraically add the moment of all such forces, then these moments should be equal to 0. So these two are the necessary conditions for a body to attain equilibrium. First condition is the resultant of all forces acting on the body must be equal to 0. Second condition is the algebraic sum of moments of all such forces acting on the body should be 0. So when these two conditions are met, then the body attains a state called equilibrium. If the body attains a state of equilibrium when it is at rest, it is called static equilibrium. And when a body attains state of equilibrium while it is continuing its motion, it is called dynamic equilibrium. Clear? Okay. Now, from the state of equilibrium, there arises a principle. Okay. So, whenever a body is in equilibrium, the sum of clockwise movements should be equal to sum of anti-clockwise movements. This principle arises from the state of equilibrium. So, one of the conditions for equilibrium was algebraic sum of moments of all forces should be equal to 0. That means all anti-clockwise movements added with all clockwise movements will cancel out each other and will be equal to 0. This is called principle of moments. That means sum of all clockwise movements will be equal to sum of all anti-clockwise movements. This is called the principle of moments. Or in other words, sum of all anti-clockwise movements plus sum of all clockwise movements is equal to 0. Or in other words, we can say the algebraic sum of moments about any axis of rotation should be equal to 0. So when a body is in equilibrium, this condition is true. What is that condition? Sum of clockwise movements is equal to sum of anti-clockwise movements, or algebraic sum of all movements should be equal to 0. This principle is called principle of moments. Okay. Now let us consider some of the daily life examples of equilibrium. So if you have seen a common balance where some vegetables you are purchasing will be placed here and a weight is placed here. So when the weight of the vegetable balances out the weight which is placed on this pan, then the pointer will be pointing vertically up and is stationary. That means this remains horizontal. So it doesn't move. So it attains equilibrium. and because it doesn't move, it is static equilibrium. Okay, so a common balance is an example of static equilibrium. Here, if you consider principle of moments, this is the clockwise movement. So this 1 kg, if suppose we are assuming 1 kg, so 1 kg into whatever is the distance, suppose we call it d. So 1 kg into d is clockwise movement, and anti-clockwise movement is again 1 kg into, this will also be same d. So they will cancel out. So clockwise movements plus anti-clockwise movements will be equal to 0, which satisfy the principle of moments. So a common balance is an example of static equilibrium. Similarly, if you consider a book that is placed on a table, the weight of the book will act perpendicularly down. That is, the mass of the book is attracted towards the earth using force of gravity. So this would be kg weight. Okay. And the table would offer a reaction which is equal and opposite. So the book which is stationary is under the action of its weight as well as reaction produced by the table. So under this action of these two set of forces, the book is stationary. So this is an example of static equilibrium again. Okay. Now if you see an aeroplane will, ignoring while landing and takeoff, it will travel horizontally along the surface of earth. So it is moving in linear motion. Okay, maybe at constant velocity. So when the aeroplane is still continuing to move, there are so many forces that are acting on it: the weight of passengers, the drag force, the drift force. There are so many forces acting on airplane. There will be engines that are fired here, so they will try to propagate aeroplane in the forward direction. So under the action of several such forces, the aeroplane is in equilibrium because it still continues its motion without any turbulence. So this is an example of dynamic equilibrium. Here the sum of moments, all clockwise and anti-clockwise moments, will be 0. That is the reason why there is no change in state of motion. Okay. Likewise, if you had considered a hammer thrower, so or suppose this is a satellite, or in other, this is, so consider a satellite that is moving about earth. So this is a case of dynamic equilibrium. It is in uniform circular motion. The satellite is in uniform circular motion, and it continues to continue like that. So this is a case of again dynamic equilibrium. See, the electrons that rotate about nucleus. This is also an example of dynamic equilibrium. Then the planetary motions like Earth revolving around Sun is an example of dynamic equilibrium. So remember these daily life examples. Okay, you might get questions about them in your end exam. Okay, clear? So we understand what is equilibrium now. Equilibrium is under the action of several forces. If a body doesn't change its state of rest or state of motion, then it is said to be in equilibrium. Equilibrium is of two types. It could be static equilibrium or dynamic equilibrium. So when a body is in equilibrium, principle of moments arises, that is, algebraic sum of all the moments should be equal to 0, or sum of clockwise movements should be equal to sum of anti-clockwise movements. And then the first necessary condition is the resultant of all such forces acting on the body should be 0. Okay. Now focus on the screen. This is an experiment to verify principle of movements. Okay, what you need to verify is sum of clockwise movements should be equal to sum of anti-clockwise movements, or sum of clockwise movements plus sum of anti-clockwise movements plus sum of clockwise movements should be equal to 0. So this is called principle of movements. So let us look at an experiment where we verify the principle of movements. Consider a meter scale. Why are we considering meter scale? Because it has uniform cross section and its density, like weight or the mass per unit centimeter cube, would be same all along the length. So it attains equilibrium when you consider such a scale. Okay. So consider a meter scale that is hung at the center using a string, and this is like tied to a rigid support. So the scale is balanced or hung at midpoint of it. So for the sake of convenience, we mark this midpoint as 0. Now take two spring balances. See, spring balance is used to measure, so there will be a meter here. It is used to measure weight, that is in kgfs. Whereas this common balance, here also you have weight, here also you have weight, but both sides when you cancel g, so you are measuring mass here. So a common balance is used to measure mass, whereas a spring balance is used to measure weight. So we are interested in measuring weight in this experiment. So that is the reason why we are taking two spring balances. So hang one spring balance to one side of the meter scale, and these are the slot weights. Slot weights are disc weights, something like this, with a slot in between. So you can slip this weight on here so that it remains stable. So such slot weights, take some arbitrary weight W1 and hang it on one side, like take this spring balance and hang it on one side of the scale. Take this reading W1 and also the arbitrary length at any arbitrary point, you just hang the spring balance. Now you take some other weight which is not necessarily equal to W1, call it W2. Now hang this weight onto the second spring balance. Now adjust L2 in such a way, by moving this point B left or right, in such a way that this meter scale remains horizontal. Okay, so you need to adjust point B by moving it left or right so that the scale remains horizontal and stable. Okay, once you attain that condition, which is nothing but equilibrium, then you take the readings of W1, W2, L1, L2. Now you multiply W1 and L1 and W2 and L2. We see that we get same movement this side and this side. Only thing is this is clockwise movement and this is anti-clockwise movement. So if you take the signature like the uh, negative sign of W2, then add them, then you will see that this will equate to 0. So you can take multiple readings considering different W1, different W2 and different L1. So arbitrary values of use arbitrary values of W1 and L1, then arbitrary value of some W2, then make adjustments so that L2, this length, like adjust B either moving it left or right, such that L2 is adjusted, and this movement, which is clockwise, L1, this is L1, and this movement, which is clockwise, will balance out this movement, which is anti-clockwise. That means scale will remain horizontal. So the scale will remain in static equilibrium. So under such condition, this movement will be, when you add the anti-clockwise movement and clockwise movement, you will get 0. So if you can repeat these experiments with different readings of W1 and L1 and W2, and you will get corresponding L2 when you attain a state of equilibrium. When you take movements on both sides and add them, you will get 0. So this verifies the principle of movement, which states that algebraic sum of all movements when the body is in equilibrium is 0. So when the scale attains horizontal position and is stable, so we are attaining equilibrium. So under equilibrium state, the sum of movement, algebraic sum of movements should equal to 0. That is what has been verified. Clear? Okay. Now let us move to center of gravity. Now consider some rock or some object. Okay. In this object, let P1, P2, P3, P4, so on until Pn be the individual particles comprising that object. Okay, infinitesimally small individual particles named P1 to Pn. Okay, now consider an arbitrary point shown with red mark here and call it x. Okay, let it be any arbitrary point x. Now measure the distance of each individual point P1, P2 from this x and call them D1, D2, D3, D4, so on till Dn. So for particle P, this is the perpendicular distance of from x. So for particle P, for these particles, let W1, W2, W3, W4 be the corresponding weights of this particle. That is, the force with which particle 1 is pulled towards the earth, let it be W1. For particle 2, let the weight with which it is pulled towards the earth is W2. So like that. So finally, let P1, P2, P3, P4, so on Pn be the small individual particles comprising the body. Let W1, W2, W3, W4, so on until Wn be the weights of corresponding to these particles. Let D1, D2, D3, D4, so on be the distance of this line of action of weight, perpendicular distance of line of action of weight from the point x for each particle. Okay, clear? Now, if we take algebraic sum of moments, so if you see, if this is considered the axis of rotation, okay, then these points all they they form clockwise movements, and these points they form anti-clockwise movements. So when you are taking algebraic sum of such movements, so delta W1 D1 plus W2 D2 plus W3 D3, so on Wn Dn, so on till Wn Dn. So this should, if it is equal to 0, then this point x is called center of gravity. So we are considering an arbitrary point x such that algebraic sum of moments of all particles comprising the body will be equal to 0. If we are finding such a point x, then this point is called center of gravity of this body. Okay, understood? So center of gravity is a point about which the algebraic sum of moments of individual particles comprising the body or mass of the body, comprising mass of the body, will be zero. So given any body, if you can find out a point about which algebraic sum of all individual particles of mass comprising that body is zero, then such a point is called center of gravity. Okay. Now, if suppose W is the collective weight of this body, so W is nothing but W1 plus W2 plus W3 so on till Wn. If W is the collective weight of such a body, then this weight can be considered as a point weight acting at Cg. So if you consider weight of this whole body to be acting at some point, then that would be your Cg. So at Cg it is considered, if the weight of the body is considered as point weight, then it acts at Cg. Okay, so this is the concept of center of gravity. So how do we define center of gravity? Center of gravity is the point about which algebraic sum of moments of particles comprising that body is zero. If the body is considered as a point weight, then this point weight acts at the center of gravity, or this point weight passes through center of gravity. Clear? Here, the center of gravity need not essentially lie within the body. Sometimes it lies outside the body. Let us see in which cases it will lie outside body. Second thing, center of gravity depends on size of the body and shape of the body. Okay, so if a body undergoes some change in shape, or it, like a car, it crashes, so it undergoes change in shape, so its Cg will shift. So center of gravity will depend on size and shape of the body, and it depends on the spread of mass. Okay, suppose you consider a cone, so the mass is more spread towards its base, so this is called spread of mass. So if you take a ship, okay, so the base of the ship is made so heavy that it doesn't capsize, so that the Cg will remain somewhere within the base. So even if you try to capsize the boat, it tends to again stand upright. So the center of gravity of any body depends on shape and its size. So when the shape changes, center of gravity might shift. Okay, and it is not essential that center of gravity should always lie within the body. It sometimes lies outside the body. But for any body, the closer the center of gravity lies or remains to the earth, closer to the earth, the more stable is the body. For example, suppose there is some body like this. So if center of gravity is here, so if there is another body, okay, and center of gravity is more near to the earth, so this body will display more stability of equilibrium. This body will be comparatively less stable. Okay, so the closer the center of gravity lies towards the earth, the greater stability of equilibrium is found. Clear? Okay, so these are the common shapes of center of gravity. So for a square, focus on the screen. For a square, the center of gravity lies at the point of intersection of diagonals. And for a circle, the center of gravity lies at the center of circle, geometric center of circle. And for a cuboid, if this is the diagonal of the cuboid from one end to the other end and from this end to the other end, so the point of intersection of such diagonals is nothing but geometric center of the cuboid. So center of gravity will lie at geometric center of cuboid. So so that will lie, if this is the length, then center of gravity will lie at L by 2 from this face, and from this face also L by 2. Okay. Likewise, for a rectangle, it is the point of intersection of diagonals. For a ring, see, the center of gravity lies at the center of the ring. Here, the CG is not lying within the body. It lies external to the body. Okay. Then, for a hollow cone, because the spread of mass is, or the mass is less, the center of gravity is at h by 3. It lies along the vertical axis, or axis drawn from vertex to the center of the base. So it lies at a height h by 3 from the base, whereas if it is a solid cone, it lies at a height h by 4. So h by 4 is less than h by 3. That means a solid cone is more stable. It displays more stability in equilibrium than the hollow cone, because the CG lies closer to the earth's surface. Okay, so for a hollow cone, the CG lies along vertical axis at a height of h by 3 from base. For a solid cone, it lies at a height of h by 4 from the base. And for a rod, solid rod, it lies at midpoint of the length. Okay, if L is the length, then it lies at L by 2 along the axis of the rod, on the axis of the rod. So for a parallelogram, so parallelogram opposite sides are parallel. So for a parallelogram, again CG lies at the point of intersection of its diagonals. Okay, and for a rhombus, again point of intersection of its diagonals. For a pipe, it lies along the central axis at midpoint of the length of the pipe. And for a sphere, it is at the geometric center of the sphere. For a triangular lamina, if you draw a median is nothing but if you join midpoint of a side to its opposite vertex, that is a median. If all such medians intersect at a point, that is the CG of a triangular lamina. For a cube, it is again the geometric center of the cube. That is, when you draw the diagonals from one corner to the opposite corner. So this point of intersection is the CG. So if h is the height of the cube, then h by 2 from each face. Okay, likewise a cylinder lies along the central axis at half the length of cylinder. Okay. So these are some of the common geometric shapes for which CG lies at the points depicted in the figures. Okay. Now, for common geometric shapes, we could get the CG from its geometry. But if suppose we have an irregular shape of object, for example, there is a lamina which is of irregular shape as shown in the figure. Okay. So if you want to know where the CG lies, so this experiment will determine the CG of such lamina. See, whenever a body is hung vertically, okay, then it swings initially, then it comes to rest. So when it is resting or when it is in equilibrium, this line of string where it is hung, the CG will lie along this line. We do not know where, but CG will definitely lie along the vertical line matching with the line of string. Okay, so this property is used to determine the CG of an irregular lamina. So if suppose we are given an irregular lamina like this, make series of holes all along its periphery. The closer to the periphery is better. So don't make a hole here, but it should be very close to the periphery, somewhere here like this. So when you make such holes, then consider a stand like this, okay, which has a peg here. Now hang this irregular lamina using this peg in the first hole and use a plumb line to draw a vertical line. So plumb line is something which has a conical weight at the bottom, and this string is tied to this peg, okay, using which this lamina is hung. So when you allow it to rest, so this string will depict the vertical line, or uh, it is the it is the vertical line at point A1. So if you draw a line along the string, so the CG is bound to be present on this line. Likewise, when you shift the lamina to the next hole and hang the lamina using B, then draw the vertical line again. Then shift it to C, then draw the vertical line again. So when you complete all the holes, you will get a series of lines that meet at one point, and this point will be the CG of the irregular lamina. Okay, so this is an experiment to determine CG of an irregular lamina. How do you determine? You make series of holes all along the periphery of the lamina. Then using a peg on a stand, you hang the lamina using first hole. Then hang a plumb line using the same peg. Then draw the vertical line along the string of the plumb line. Then you hang the lamina with next hole and repeat the experiment and draw the line along the vertical string. So when you complete all the holes, you will get a series of lines that intersect at one point, which will be the center of gravity of this lamina. Okay. Okay, so that's all for today. We'll stop here.